This is a joint paper with Caterina Consani, and the title of the paper is The Hyperring of Adele Classes. Okay, so the Adele class space, given a global field K, is simply the quotient of the Adeles over K by the multiplicative group of K. That's all it is. And I mean, it is a space which is a very delicate space. It's a non-commutative space. And it has been used in two different ways. The first use was to obtain a spectral realization of the zeros of L functions. And the second use of this space was to give a trace formula interpretation for the explicit formulas. Okay, but somehow, if you want, very recently, in a previous work with Consani, we noticed that, in fact, already a non-trivial algebraic structure was very useful on this space, namely the space of Adele classes. And this structure came about by this general theory which has to do with characteristic 1, which was essentially initiated by Jacques Tits, and which at first has been formulated as the theory of the field with one element, which was denoted by F1, the kind of limit case of the field, the finite field Fp for p equals 1. And what we noticed in a previous work is that the fact that this is not only a space, but that it has a natural structure of monoid is extremely useful because in the spectral realization of zeros of L functions, there was something which looked a little bit unnatural, but which becomes extremely natural when you think of this as a monoid, and when you look at the points of the projective line over F1, which are rational over this monoid. So if I call this M, if you want, you look at the points which are rational over this monoid, and then what you obtain is that you obtain that the spectral realization is in fact just the first cohomology group of a certain sheaf on the space P1F1. However, if you want, what was totally open was that the monoid structure is all right, but it ignores the additive structure. So it's a rather weak structure. And for a long time, we were looking, if you want, for something that would take into account the additive structure and that would allow to do arithmetic on this space. So now, the great surprise is that the answer to this puzzle of finding the right type of additive structure is in fact contained, I mean the germ of it, if you want, is in fact contained in a paper by Mark Krasner, which appeared in the same volume as the paper of Jacques Tits, which initiated the subject. So it's a volume which goes back to 1956, and in which the two papers are essentially contiguous. The discovery of Krasner, if you want, of hyperfields can be explained in a very, very simple manner as follows. When we do arithmetic, we use the elementary operations of addition, subtraction, multiplication, and division. And if you want to give the simplest example of an arithmetic realm, you can talk about the field with two elements, where the best way to explain things is by the properties of numbers to be even or odd. For instance, okay, you know, the product of even by odd will be even, and so on. And so you can write extremely easily the tables. Now, consider the following properties of numbers, that they are zero or non-zero. And what you will obtain, in the same way, you will very easily obtain the multiplication table. But you will find out that when you write down the addition table, what can happen is that when you add two non-zero numbers, the result can be zero or non-zero. So if you want, you get what is called an hyperoperation. And Krasner has been able, in his paper in 1956, to really extract the correct axioms for these algebraic objects. And you see, these algebraic objects look very trivial at first, because after all, it's formed with two elements, 0 and 1. But you find out very quickly, this is what we found in the paper, in our paper, two things which are quite remarkable. The first one, which was in fact noticed by Prenovitz a long time ago and which we recast in the language of hyperfields, is that vector spaces over the Krasner hyperfield, when you look at them, you find out that they are exactly the projective geometries, exactly the axioms of ordinary projective geometry, in which lines have at least 4 points. So in fact, this allows to connect with the work of German geometers after the war, like Karzel and Ehlers, and it opens up an amazing source of results on the extensions of the Krasner hyperfield. And in fact, when you try to classify even the finite extensions of the Krasner hyperfield, you find that it is an open problem, and that if you want, the fact that such extensions would be only restricted to the obvious one is equivalent to an open conjecture on the fact that homogeneous, finite, non-Desarguesian projective planes do not exist, which is a very difficult open problem in combinatorics. Our key observation in this paper with Consani is the following, is that in a sense, if you want, this Krasner hyperfield, which has 2 elements, is a sort of already enhanced and upgraded version of the idea of teeth on the field with 1 element. In the case of Krasner, you don't say that 0 is equal to 1, but you make a more subtle addition. Now, our key observation was the following, is that Krasner had already observed that there is a sort of rather easy way to construct hyperrings, which are the obvious generalization of hyperfields, which is to consider the quotient of an ordinary ring by a group. Now, what we proved, which is a very important lemma, is that for such a hyperring to contain the Krasner hyperfield, to have, if you want, as a prime sub-hyperfield, the Krasner hyperfield, it's necessary and sufficient that the subgroup by which you divide, the subgroup, group of units by which you divide the ring, is such that when you adjoin 0 to this subgroup, you obtain a subfield. And amazingly, this is exactly what happens for the Adele class space. Because the Adele class space is the quotient of the ring of Adeles by the multiplicative group of the subfield. So when you adjoin 0, you really have a subfield, and we know very well that when you use the Poisson formula to prove the functional equation, that's exactly the key. That's the core of the argument. So this observation told us that, in fact, the structure discovered by Krasner, which, by the way, was motivated by class field theory, should be the key in understanding the algebraic nature of the Adele class space. Okay, so let me now come to the main result of this paper, which is the following, which is that now that, if you want, we have found the correct arithmetic structure on the Adele class space, we have found that it is a hyperring, then we can do arithmetic. And in particular, you can define what is a prime ideal, of course, and you find the right spectrum. And you can also define what is a prime element. And what we discovered, and which is explained at the end of the paper, is the following, is that, first of all, for any global field K, if you look at the prime elements, a set of prime elements in the hyperring of Adele classes, you find out that it's naturally a groupoid. So it has a structure, and this structure is a structure of a groupoid. Moreover, if you consider the special case when the global field has non-zero characteristic, in which case it is a function field over a curve x, then it turns out that there is a canonical isomorphism between the groupoid of prime elements of the hyperring of Adele classes and the loop groupoid of the abelian cover of the curve, which is associated to the maximal abelian extension of the original global field. Now, the reason why this is very interesting is the following, is that when the characteristic of the field happens to be 0, there is no known geometric replacement for the curve, but the hyperring of Adele class continues to exist. And so now, thanks to this result, we have a very precious indication on the geometric mysterious object which we are looking for, which replaces the curve, which is that we know the loop groupoid of the maximal abelian cover.